So in this module we're going to see application of power series and some ways to get more power series representation of functions. And we're going to start with something we discussed a little bit before in the previous module, which is how to find the exact sum for certain numerical series using power series. So among the standard functions for which we have found power series representation, at the end in the last video of the previous module we had concluded with this list of standard representation by power series of standard function, specifically for the sum of a geometric series, sine x, cosine x, natural exponential, ln of 1 plus x for x between -1 and 1, and arctangent x for x between -1 and 1. So if we keep this in mind and we are looking for the exact sum of a particular series, if we're not looking for just a justification of convergence but the actual sum, the exact sum, then maybe we can find that by matching the numerical series with a specific value of a function for which we have a power series representation. So for instance, for this series from 0 to infinity of 3 to the n over 5 to the n factorial, if we rewrite the 3 to the n over 5 to the n as 3/5 to the n, what we have is a series of 1 over n factorial multiplied by something to the n, and that should remind you of the power series representation of e to the x, which is the power series starting at 0 of general term x to the n over n factorial. So here what we have is exactly this when x is 3/5, and since the power series representation for the exponential is valid for all x, it is in particular for x equals 3/5, so this is nothing but the value of the exponential function at 3/5, e to the 3/5. Another example, we want to find the exact sum of the series from 0 to infinity of -pi squared to the n divided by 36 to the n multiplied by 2n factorial. So this looks complicated, but again, keep in mind that we are asked to find the exact sum, so probably this should be something that we can do by simply matching with standard power series representation for standard functions. In this case, in particular, there is a 2n factorial at the bottom, and so maybe that means that this corresponds to a cosine, or at least we can try to match it with the formula for a cosine, because in the power series representation for cosine x we have 2n factorial at the bottom. So what we're looking for now is the value of x, so we want a certain value that is raised to the power 2n. Well, we can rewrite our expression with this in mind, where we want to have a power 2n appear. And when we have this -pi squared to the n, we can write that as -1 to the n, pi squared to the n, and pi squared to the n is really pi to the 2n. So here we have something to the 2n, that's good. As for the bottom, we have 36 to the n. 36 is a square, it's 6 squared. And 6 squared to the n is really 6 to the 2n. So we end up with pi to the 2n at the top, 6 to the 2n at the bottom. If we put that together, it's going to be pi over 6 to the 2n, and that's exactly what we want. And additionally, we got the -1 to the n that we needed for the expression for cosine x. So we end up with a series from 0 to infinity of -1 to the n divided by 2n factorial multiplied by pi over 6 to the 2n. That's exactly matching the power series representation for cosine x when x is pi over 6. And the power series representation for cosine x is valid for all x, in particular for x equal pi over 6. So that means what we have here is really cosine of pi over 6, which is square root of 3 over 2. Another example, we want to find the exact sum of the alternating series from 0 to infinity of -1 to the n divided by 2n plus 1. Well, this 2n plus 1 at the bottom should remind you of the power series representation for arctangent x, which is valid for x between -1 and 1, with the endpoints included. And you see that if you plug x equal 1 in this power series representation, you get exactly the numerical series we're looking for. So this is arctangent 1 because we have said that our power series representation is valid at -1 and 1. And arctangent 1 is just pi over 4. This is the value of the angle where the tangent is equal to 1, so that's pi over 4. Let's look at the example where we want to find the exact sum of the series from 0 to infinity of -1 to the n, 2 to the power 4n divided by n factorial. So again, if we're going to try to match with one of our formulas, you have this n factorial, which might suggest that you use an exponential. But in that case, we need to have something raised to the power n. So we are going to rewrite our -1 to the n, 2 to the 4n as a single, a power n of a single number, simply because 2 to the 4n is really 2 to the 4th that you raise to the power n, and then -1 to the power n multiplied by 2 to the 4th to the power n is really -2 to the 4th to the power n. And so what we obtain matches the formula for the exponential function. And since the power series representation for e to the x is valid for all x, it is in particular for x equal -2 to the 4th. So what we get is e to the power -2 to the 4th, which is -16. So we get e to the -16 for the sum of this series. Now, instead of a closed form formula, we start with the first few terms of a series. 1 minus natural log of 2 plus natural log of 2 squared over 2 factorial minus natural log of 2 cubed over 3 factorial plus natural log of 2 to the 4th over 4 factorial, and so on. So it seems that we have terms to the power n divided by n factorial, so that suggests to use again the power series representation for the natural exponential function. And specifically, you see that if you use x equal negative natural log of 2, then when you raise it to the n, you get -1 to the n, natural log of 2 to the n. And so what we have here is really just the value of the exponential function at -ln of 2. Of course, -ln of 2 can be written natural log of 2 to the -1, that's one of the logarithm law. And now I have the natural exponential of a natural log, so that's the identity, and 2 to the -1 is 1/2. So the sum of this numerical series is exactly 1/2. Let's look at one more example where we want to find the exact sum of the series from 1 to infinity of -1 to the n plus 1 divided by 3 to the n. So again, among the candidates we have on the left-hand side, in the column on the left, we have the power series representation for natural log of 1 plus x. That is a power series representation where we have a n at the bottom. And so we can try to match this formula, and for that we need a power nth power of an x, and we have this -1 to the n minus 1. In our formula here we have -1 to the n plus 1, but in fact -1 to the n minus 1 or to the n plus 1 is the same thing, because n plus 1 is odd exactly when n minus 1 is odd, and therefore -1 to the n plus 1 and -1 to the n minus 1 are just the same thing. So we can rewrite the general term of our series as -1 to the n minus 1 divided by n, and then this 1 over 3 to the n can be written 1/3 to the n. So under this form, this matches the power series representation for natural log of 1 plus x in the case where x is 1/3, and 1/3 is in the interval where this is valid, namely from -1 to 1, where we exclude -1 and include 1. And therefore this is the value of the function 1 plus x at 1/3, ln of 1 plus x at 1/3, namely natural log of 4/3. Now turn to the next video where we're going to look at other kinds of applications.